just a minute, I call it fidget here. We want to keep on expanding our minds. And at this point, we want to start talking about gases a bit. So, what is a gas? A gas is just a collection of molecules that kind of move around. Whatever container you put them in, they spread out and occupy the volume of that container, bouncing around off the walls of the container and interacting with each other, bouncing off each other, and all sorts of things. There's some temperature that the gas is at, some volume that is contained within, and there's also some pressure that the gas exerts on the walls of the container. So we want to start talking about those things and making some general conclusions about them. So, temperature, we have an understanding of what that is. For gases, the temperature of a gas really comes down mostly to how quickly the molecules are moving around. And well, there could be some other things with them spinning around and vibrating too, if they're polyatomic molecules. But we'll just stick with monatomic molecules, molecules that just have, really, not being atomic, that are just one atom. Anyways, that's temperature. Temperature associated with the rate of motion, the average rate of motion of the molecules. So, gases. Temperature of a gas is directly related to motion of its particles. How fast they move around, so to say. And then we've also got ourselves volume. Volume of a gas is determined by volume of the container which it resides. So gas will always expand to fill its container. So it's spreading out, doing what it does. So we've got temperature, volume, and then we've also got ourselves pressure. Pressure of a gas is a measure of force per unit area. That it exerts on walls of this container. That's it. That's what pressure is. Pressure is force per unit area. Pressure of a gas is, well, what's the force that it's exerting on average spread out throughout the container on its walls. So really, what do you have? You have some sort of container. You could take like some balloon, it doesn't really look like a balloon, but some container. You can take little molecules in here, zipping around. This one's going that way, this one's going that way, this one's going that way. How many am I going to draw? I don't know. But they're kind of moving around randomly. Sometimes they come close to one another and move in different directions. Some are going slow, some are going fast, all sorts of different molecular speeds, but there's some average rate overall. And what are they doing? Well, they're striking the walls and they're bouncing off. They're bouncing off each other. all around, and that bouncing off of the walls is them exerting a force on the walls. And well, there's this many particles. Assume that there's a whole bunch of them, like a whole bunch, millions maybe. And we have that the walls are constantly being struck by these particles. And the particles then exerting a force on the walls, and that force exerted over the area of the walls is the pressure that the gas exerts. Fantastic. Well, there's some interrelation between the molecules, their molecular speeds, their temperature, if you will, the volume that contains them, and the pressure that they exert on the walls of the container. There's a relation between those. Equation that relates temperature pressure, volume of a gas. Some number of particles is called the equation of state. Pressure, volume, and temperature are what are known as state variables. It's the state of the gas. What state is it in? What pressure does it exert? What temperature is it at? What volume is it confined by? Those are state variables. So we call it the equation of state. And well, that equation of state can be very complicated. It depends on certain aspects of the gas. It depends on, is it a monoatomic gas? Is it polyatomic? What sort of temperatures are we looking at? What sort of pressures are we looking at? Do the particles have effects on one another other than just coming close and colliding? That is, are they charged particles maybe? Charged particles exerting long-range forces on one another. How big are the particles? There's all sorts of things that can make the equation of state very complicated. Is there chemical energy associated with the system? Ooh. We want to keep things simple here. And what we do is we come up with what's known as an ideal gas. Idealize the situation to have certain constraints and then talk about the ideal gas law, which is the equation of state for an ideal gas relating the pressure, the temperature, and the volume of some number of molecules composing an ideal gas. So the question becomes, what is an ideal gas? What makes it ideal? Ultimately, gases, most gases, I should say a lot of gases, at low pressure and low density behave fairly well in terms of an ideal gas. We find that a lot of gases at atmospheric pressure, at room temperature, behave very nearly like an ideal gas. Not all gases, but a lot of them. So it's a good little gas law, but it does have some idealizations. So, ideal gas. What is an ideal gas? Well, that has some restrictions on what it is. The size of the particles, are, should we say, negligible to the amount of space contained by the gas? No. Let me say something else here. The size of the particles. The size is good. The size of the particles is such that volume that they individually occupy is not relevant. Considering volume which contains them. That is my fancy way of saying their size is negligible. You can kind of ignore their spatial extent. They themselves occupy negligible space. So the majority of the volume is the actual volume of the container. All right, that one's a little bit of a stretch, but gases at low density will not occupy that much space overall. Anyways, we got that. We've also got that, put a little hash mark there. There are no long-range forces between particles. Like gravitational forces, and electromagnetic. Those are considered long-range forces. So all matter, all mass is attracted to other mass. I'm assuming that that is negligible or not relevant. In electromagnetic forces, if they were charged particles, we'd start having long-range electromagnetic forces, charge forces, and we're assuming that that's not the case. Any collisions? Between the particles and or the walls of the container are elastic collisions. We've looked at elastic collisions before, right? What is an elastic collision? Momentum's conserved and kinetic energy is conserved. Collision. So there's no changes in kinetic energy when they collide overall with either the walls of the container or themselves, and momentum's a conserved quantity. So these are the general criteria for an ideal gas, and taking that into consideration, or taking that to be the case, we've got what is known as ideal gas law. All right, so the ideal gas law. This is the equation of state for an ideal gas. It says this: PV is equal to nRT. All right, so we need to know what all these are. There's a couple different ways of writing this out, actually. Let me just put an or. PV is equal to N times K sub B times T. These two are the same expressions, but there's some different things going on between them. All right, so for this one, for them both, P is the pressure. We have V is volume. Volume that it occupies, we just say that's the volume of the gas. T is the temperature. of the gas. And then we've got some of these other things going on here. We've got an N and an R, and a capital N in the case of B. N, lowercase n, is the number of moles. Number of moles of the gas. So that's a convenient way of quantifying how many particles there are. 1 mole is equal to 6.022 times 10 to the 23rd particles. It's Avogadro's number, right? So we could talk about, hey, we have 2 moles of a gas, that's how many particles it would have. And then we've got ourselves R here. R is known as the universal gas constant. And well, what is R? R depends, actually. It depends on what sort of unitizations you're using. R is equal to 8.314 joules per mole Kelvin. And R is equal to 0.081121, shoot, 0.0812, I'm gonna have to go back and verify that, forget that. But this is atmosphere. That's the joules. This R. Atmosphere liters per mole Kelvin. So notice there is a distinct difference between the unitizations of these 2 different R's, and thus we've got different numeric values for them as well. Both have the mole Kelvin, that's good, but this one has joules, this one has atmosphere liters, ATM, L. So a lot of times, especially in chemistry, when utilizing this stuff, you're measuring the pressure in atmospheres, how many atmospheres of pressure, and you're measuring the volume in liters. How many liters of a gas do you have? Well, that's great, but in SI units, which would give us this joules here, that's not how we measure, say, pressure and volume. In SI units, the units of pressure are equal to, what's force per unit area? So we say it's equal to the units of force per unit area, which is then newtons per meter squared. Which is what we call pascals. Use a capital PA for pascals. And we've got that SI unit of volume is, well, how do we get volume? Length times width times height. What do we measure length in terms of SI units? Yeah, just meters, right? Cubic meters. There we go. Well, atmospheres and liters can be converted into pascals and cubic meters. Those conversion factors form, but really what we have is just 2 different R's depending on what sort of values you have the pressure and the volume in. Temperature, we need temperature in Kelvin in those expressions there. Temperature must be in Kelvin. Must be in Kelvin. But if we're given the pressure and the volume in pascals and cubic meters, we use this for the universal gas constant. If we're given the pressure and the volume in atmospheres and liters, then we use this for the universal gas constant. And that's it. And then it comes into just utilizing this. It's still the number of moles, the temperature, the pressure, and the volume, and the R there, universal gas constant. All right, so that's for the first one. For the second one, notice it's a little bit different. We've got pressure and volume, and then we've got a capital N and a K. This one I have to be a little bit more careful with. Now, N is the actual number of particles of which the gas is comprised. How many individual particles are there? Usually it's a really big number, so a lot of times, yeah, we're utilizing the number of moles, but if you have the actual number, then hey, you can use that second expression, PV equals N K sub B times T, which then begs the question, well, what's K sub B? K sub B, it's a bad B. Bad B. K sub B is Boltzmann's constant. Boltzmann's. Ludwig Boltzmann was an Austrian physicist that did lots of things with thermodynamics, electrodynamics, among other things. Brilliant guy. But he's got this constant, K sub B. Oh my gosh. K sub B is equal to 1.38 times 10 to the negative 23 joules per Kelvin. Don't need any moles there because we're talking about pure number of particles here. But this, if you're using K sub B, is demanding that you are using SI units for pressure and volume. Can't use it with the others without reconfiguring what this value is, and we don't want to do that. So this is what we've got. Got this equation of state that relates, again, pressure, volume, and the temperature to some other things that generally we're going to keep constant. The number of particles or the number of moles, and K sub B in both are constant values for these systems. So what do we have? Well, we've got something where we can look at pressure variations in terms of changing volumes and or changing temperatures. We can look at volume variations in terms of changing pressures and temperatures if something's allowed, a gas is allowed to contract and expand in its container. And we can look at how the temperature may change with variations of volume or pressure. There's all sorts of things that we can do with that. But those are nice expressions there, and that's what we got. An ideal gas law. Yep, I was wrong. 0.0821, not 12. Sorry about that. Make that little change there, and move onward. Thanks.